All right, another Physics Teachers Are Awesome video. This time it's a video that has chapter markers, and so I kind of looked at the chapters and thought, hey, these two chapters towards the end sound really, really interesting. You can see that this is for, hang on.
All right, well, anyway, let's try an example. Take a moment, try this example.
There, sorry. You can see it's for an AP Chemistry class, and they're doing waves, wavelength, frequency, and energy, and it looks like it's all about light. So let's get started.
Example, and then so now we're calculating the energy of one photon of yellow light, and we're given wavelength in nanometers. Oh, notice we're given nanometers. We got to take a moment and convert nanometers to meters, because before plugging into this equation, we need wavelength in meters since C has units of meters per second.
Cool.
Now that I have my wavelength in meters, if I plug in to solve for frequency, I'll notice that meters cancel out and I get my frequency in 1 over seconds, or seconds minus ones, or hertz.
Cool. So let's talk about, just sort of smashing those things onto the screen as you go, as opposed to, writing them or doing one at a time. So keep in mind, this is 14 minutes, almost 15 minutes into the video. So a lot of this, I think, based on the chapter names, here, we can take a look at the chapter names here. Can you read those? How to use it, right? So there's 5 minutes on how to use the equation. And there's some notes about how to use some issues around the calculator, especially with scientific notation. So it's useful to realize that some of this they've been prepped for. So they're prepped for it, and now we're seeing it. And so it's really kind of great to say, okay, now let's put it into action. A couple of things here, I don't think students have any sort of experience with these kind of exponents, right? So I guess in a chemistry class, you're used to even bigger exponents. But at some point, it's like, I have no idea what that means. Let's just move forward. Imagining something wiggling that often, it's just hard to imagine, right? And so what's happening here, of course, is we're trying to get the frequency so that we can use, probably Planck's constant will come next, to figure out the energy.
Now I can go one step further and calculate the energy. I can calculate the energy now that I have the frequency. Again, I had to get frequency first because my energy equation is in terms of frequency, not in terms of wavelength.
Just want to pause for a second there. I was talking to my own kid who is in a high school math class right now, and he was kind of complaining that the instructor often will start with the point slope formula before deriving any other formulas for the line. And he just like, why can't we just jump to that formula? So we were talking about sort of what do we want students to be able to do. So what happens here, of course, is that we're using standard forms of a lot of these equations. Take these two here, this one and this one, right? Well, I can remember in times past when I've offered to students an opportunity to nominate equations for, I don't know, a cheat sheet or some equations that they want at the top of an exam or a quiz or something. And there was a day when somebody nominated this equation. And I said, okay, great. Does everyone approve? Does everyone like that equation? And then someone nominated this equation. I'm like, okay, fantastic. I don't quite see why we would need to do that, but what do you guys think? And it was such an interesting conversation in the class because to me, these two are the same, right? There's no difference between these two. But there's this idea of how much algebra do we want students to have sort of in their brain to sort of a cognitive load issue so that they can get to some interesting physics, right? And so essentially the students were all arguing with each other. Now, of course, I built in an artificial problem where I said, well, I think there's only room for 10 equations for this exam. And so there were students saying, oh my gosh, if we only have 10, let's not waste 2 of them on this. Let's just put 1 in. And of course, then somebody nominated, let's see, what would it be? Lambda equals C over nu, right? And people just kind of groaned. But it's interesting to think about that cognitive load stuff. And so, I think that there's some people who would have said, oh, well, if you give me lambda, I can just use HC over lambda for the energy. But if this is really how you're representing it, I think it's totally fine to get students to think, okay, well, hey, if I give you something, you're going to have to monkey with it a little bit until you get some frequency, because frequency is how we think of energy.
So I have H for my formula sheet. Plug in with units so you can see how things cancel. Here is my frequency I just solved for, and I'll notice the seconds cancel, and I get my units of joules. They don't specify units, so leaving my answer in joules is completely acceptable. And let's always be aware of sig fig. This has 3, so this should have 3.
And of course, we would expect the energy of one photon to be an itsy-bitsy tiny amount of energy. And so that's, again, these gigantic exponents. In a chemistry class, I think they're used to gigantic exponents, and of course, in physics, we would almost immediately write this in electron volts because that's really on the scale of single photons and single energy transitions.
And that's my answer. If they ask for a photon, this is the energy that a photon of this frequency and therefore of this wavelength carry in joules. Atom. Now that we've calculated the energy of a single photon, what if a question asks for calculate the energy supplied by 1 mole of photon? Interesting. Same way.
Oops. Let me just go back. There we go. So, I mean, this is exactly what I was talking about. In chemistry, they're used to gigantic exponents, and this is such an interesting question. I don't know if I've ever contemplated a mole of photons before. And so we saw the answer. We can see what's going to happen here. This is going to be absolutely a macroscopic amount of energy. And so if you think about when you see a macroscopic effect of light, burning something or lighting a fire, or I was just thinking about like a really bright laser or something. When there's a macroscopic effect, like it hurts or I can see it, we need, it can't possibly be single photon effects. It's got to be, lots and lots of photons. And so the question is, what would a mole of photons do? Very interesting.
Supplied by 1 mole of photon. Interesting. Same wavelength as the other problem. So this is the energy of a single photon. What if they asked for the energy of 2 photons? What would you do? I would just multiply that answer by 2. Okay. What if they asked for 3 photons?
Awesome.
I multiply by 3.
Perfect.
What if they asked for a dozen? I multiply by 12. Okay, well, now they're asking me for a mole. So what would I multiply by? Avogadro's number, 6.022 times 10 to the 23rd. So I would just scale up by a factor of Avogadro's number. Now, it might be helpful whenever you have this amount of energy, we know it's per single photon. It might be helpful if you want to show this with like dimensional analysis to write that as not just joules, but joules per photon. And if I write it that way, I can see how I can easily get into joules per mole rather than joules per photon. If I say that.
So that's interesting, right? So the way I think I would have done this is I just would have done joules times, how would I have thought about that? Yeah, I think I would have just done exactly the 2, 3 dozen examples. You said, oh, well, there's this many, so we just multiply. But to put in this sort of dummy unit of photons helps to really, especially when students are used to this kind of construction where they just want all their stuff to cancel so they can understand what eventually it's going to be talking about. So I think that's really, really interesting, getting students to understand that if you're used to this kind of construction, there's ways to think about doing it that way. What was the other thing? Oh, yeah, just about, again, thinking about these itsy-bitsy exponents and these gigantic exponents. I remember taking chemistry in high school when it just suddenly dawned on me that, I just needed to read the question long enough to know if it wanted a gigantic answer or if it wanted a teeny tiny answer. And that's how I knew where to put Avogadro's number. Is it going to go in the numerator or is it going to go in the denominator?
There's 6.022 times 10 to the 23rd photons in 1 mole of photons. Photons cancel out. I multiply these two numbers, and I get my answer in joules per mole. Now, they might also ask me instead of joules.
So 200,000 joules. Let's take somebody who weighs 100 kilograms. Boy, I wish. And let's raise them how many meters to get mgh to be equal to 200,000. So they're already 100 kilograms. G is another 10, so that's 1,000. So I need to go up 100 meters. So a 10-story building. So if I'm more than 100 kilograms, fine, whatever. But anyways, if I were to walk up a 10-story building, walk the stairs up a 10-story building, the amount of energy that it would take for me to do that is in the vicinity of 200,000 joules. So if there was a laser that was powerful enough to, let's say, hit the ground below me to cause an explosion, so we're converting that light energy into some sort of explosive energy on the ground, to knock me 10 stories high, whoof, that's a laser. So this is actually, a mole of photons is really quite a bit.
Joules per mole, then I might ask for kilojoules per mole. And then I would just have to essentially, I would just end up, dividing my answer by 1,000 to get into kilojoules per mole, which you might see them ask in problems. So those are all these little equations and the things that you might get asked about it. You got to know your C equals.
Oops, I just want to go back here. So I just realized I made a mistake. I forgot about this too. So it's a 20-story building. My gosh. Wow. Hope I did that math right. Check me, please. So I really, really liked this. I loved the fact that there's all of these chapters to scaffold how to do this. And imagine if you're watching this, you say, oh, I can't remember how to do that equation. Oh, here's an entire chapter how to do that equation. My calculator is not working for me. Oh, there's an entire section on calculator. So I do really like this, and I know that there's a lot of learning management systems whose video storage allows you to put notes kind of anywhere you want after the fact, and that's actually really, really useful. I know that I just basically don't do it because I'm just constantly just trying to do one-take wonders, right? Just go, go, go. But I think that I'm super fascinated by this extra bit of post-processing that can be done. And of course, there was some pre-processing done too, because all of these slides had been made before she started making the recording. I really liked this construction. This was really, really cool. I just think that helping students understand how a new calculation is connected to stuff they're used to is really interesting. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.